Hello everybody, welcome to our video solutions for Superquiz 1. This is from Fall 2022 Math 350 at Cal State Fullerton. The first couple of problems are going to be about sets, right? We're looking at some naive set theory. We want to make sure we understand unions, intersections, what it means to be a subset or an element, what is the empty set, etc. So in the first problem, we're looking to find a non-empty, okay, so that means it's not equal to the empty set, proper subset. Okay, so subset, generally we could write it like so, but as soon as you say proper subset, now you mean, I don't want it to be equal, so I use this symbol, or occasionally we can use this symbol to say it's not equal. Of, so this is a union followed by an intersection. So let's compute this union here, right? We have the interval 1 to 3, the interval 2 to 7. Maybe we'll draw a little picture. And say, all right, so here's 1 and here's 3, and I want everything between 1 and 3. And then I need the union, so I get to put both sets together with 2 to 7. So let's see, 2 is going to be here, and maybe 7 can be over here. And so all the elements in there, I can just keep coloring in yellow because I get everything. So I get everything between 1 and 7, but I don't get to include 7, although I do get to include 1. So this union would equal the half-closed, half-open interval 1, 7. Now, once I've computed that, I need to do the intersection with 2, 6, which means I need everything that's in both 1, 7 and in 2, 6. So let's sketch 2, 6. Well, we already have the 2 on here, but now I get to do the closed, and I go to 6, and I say, what's the stuff in both of them? Well, let me sketch 2, 6 in green, and I say, well, all that green is inside the yellow I already had. In fact, this 2, 6 is a subset of this union we had already, 1, 7. And so this 2, 6 actually is the intersection. So the intersection is simply 2, 6, including the 2, not including the 6. Now, if we stopped here, we're doing okay, except we haven't answered the question. Remember, we're trying to find a non-empty proper subset of this intersection, namely of 2, 6. And of course, there's a lot of ways to do that. I just need to get rid of some points. So one simple way is we'll get rid of the 2. There you go. It's not empty, it's proper. Does not contain all the elements. Or maybe I want to make it really look obvious, so I go something like, 3 to 5. Or maybe I get rid of the 3 and the 5. Or maybe I just write down a single point. That's non-empty, has a point, and it's proper. Doesn't have to be an interval, just a subset. Of course, if I wrote down the empty set, that wouldn't work. If I wrote down 2, 6, including the 2, that doesn't work either. Okay, so let's move on to problem 2. In problem 2, we have true-false statements. Nice. And they're all about the empty set. So let's see. The first one says the empty set has no elements. Well, that's absolutely true. That's what defines the empty set. It's the set with no elements. So that's good. That's a true statement. The next one, the empty set has no subsets. Well, this seems pretty reasonable, right? If it has no elements, how is it supposed to have any subsets? However, if I consider the empty set as a subset, does that make sense? Well, for the empty set to be a subset of the empty set, it would have to be that every element of the empty set is an element of the empty set. Well, this is vacuously true. The empty set has no elements. There's no condition to actually check. It just holds automatically. So in fact, the empty set is a subset of the empty set. And so this is a false statement, right? The empty set has at least one subset. In fact, it has only one subset. Okay, the next one, the empty set is never a subset of another set. Well, this example shows that that statement is false. The empty set is a subset of itself. And finally, the empty set is always a subset of every set. So I'm asking, is the empty set a subset of every set? And the answer is the same as it was in 2b. Yes, because there's nothing to check. If I ask for every element of the empty set to be an element of S, it's vacuously true because there are no elements in the empty set. So in fact, the empty set is always a subset of every set. So this is true. Okay, moving on to problem 3. In problem 3, we're looking for 3 examples. We don't need to justify them, although I might say a few words here, of functions whose domain and codomain are the real numbers. Now, it's very important here that when you go to write down one of these functions, that you have the domain be the real numbers. I anticipate when I look at the exams that there's probably going to be several people who just change the domain on me, right? So, I'm going to use the domain as the integers, okay? Well, that's not good enough, right? Like, we're actually asking for a function whose domain is all the real numbers here. All right, so let's try to do some examples. So, the first one, we're looking for a function on the reals that is injective and not surjective. All right, well, let me show you a couple of examples. Now, I would have been quite fine if you even just graphed such a thing, all right? So you can describe the function not with an explicit rule, but at least with a graph. So let's try that. So here's kind of a nice one. If I want it to be injective, then of course I can't have any repeat output values, right? So here's going to be my y-axis, my x-axis. But I don't want it to hit every single y value. So what I might try to do then is put some, say, an upper and a lower bound on my function. So I say, well, it's never going to go above or below these 2 lines, and therefore it can't be surjective. It's not going to hit all the real numbers. Okay, and then in order to make it injective, I'm going to make it, say, an always increasing function. So here's increasing, 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 but then it levels off, but it's still increasing. Right? Okay, this doesn't look very good on this side, but hopefully you get the idea of what I'm trying to do here. And so what would be maybe a function that does that? Well, this could be f of x equals the arctan of x. So that would be an example. How about another example? Maybe you don't remember all your graphs of inverse trig functions. Well, what if we just did the following? What if I took y equals x, okay, and then I stop when I get to 0, and then it's going to hop up to, I don't know, say 1. And then it's going to continue at the same slope, but now just 1 higher. So this is not a surjective function because it is missing the values between 0 and 1, but it is injective because it's not repeating any values. So here, g of x is a piecewise defined function. It's just defined to be x when x is less than or equal to 0, and it's defined to be x plus 1 when x is greater than 0. All right, so there we go. There's a couple of nice examples. Oh, heck, let's just do one more, right, just for fun. Okay, maybe this is the easiest of them all. So what if I draw an increasing function which never crosses the x-axis? So we know it's injective because it's increasing, and we know it's not surjective because it misses all the negatives. What, oh, I called this g, but this is, again, another f. What function could this be? Well, this could be e to the x, for example. Okay, so we got a bunch of examples. Some of these are, very common. Some of these are less common, but still important. Others, okay, a little more thrown together ad hoc, right? It doesn't matter. The point is just you can do it. All right, let's try the second one. Now we want to find a function that is surjective, but not injective. Okay, well, let's see. So for B, we want one which is surjective and not injective. Well, I guess kind of an easy way to do this is to take x cubed. Okay, now x cubed won't satisfy the problem, but let me just quickly draw x cubed. So you see this is the one that's going to come up, it's going to be right there, it has this inflection, but then it just turns around and goes up again. Okay, so this is y equals x cubed. And that doesn't satisfy the problem. It is surjective, but it's also injective, right? It never repeats any values. But if I can just inflate the middle a little bit so that it goes something more like this, right? So it actually does go up and then goes down. Well, now this is still surjective, but it will not be injective, right? It's repeating some values. In fact, I can make sure that it repeats values by just making sure that I have, say, 3 roots, right? I don't need to necessarily have 3, but I could do 2. But hey, I could do 3. So in fact, I could say, well, what if this was -1, that's 0, and that's 1, which I could get by doing, so now g of x equals, well, let's see. I want it to hit at 0, so let me put an x. I want it to hit at -1, so let me put an x plus 1. And I want it to hit at 1, so let me put an x minus 1. Okay, and I could expand this if I wanted to see it written in full. So let's see, this bit will be x squared minus 1. And so in total, I get x cubed minus x. All right, so that would seem to do it. Okay, let's do another one. How about, let's see. Well, if I want to lose injectivity, like one of the most not injective functions is a periodic function, right? Like the sine function. The problem with the sine function is it's definitely not going to be surjective. But what I could do is I could add to the sine function, say, some increasing function like x. All right, now, in order to make sure this looks good, what if I make it, instead of sine of x, I make it 2 sine of x? That gives me a pretty big amplitude going on. So if I do x, so if I do g of x equals x plus twice sine of x. So it's going to look like 2 sine of x, which will be nice big wave function, but then this x is going to make it go up all the time. So it's going to look something like, well, okay, it's going to, I don't want to make sure it's going to cross here, but it's going to look something like this. All right, and it'll keep having ups and downs, right, as you go through it, because you get a little sine function, but now you're increasing it all the time with this x. So there's a way you could do it. Okay, so moving on to the final one, we want a function, again, the domain is the reals, that is neither injective nor surjective. Okay. Well, let's use one of our most basic functions. How about we try y equals x squared? So just a nice parabola. So here we'll have h of x equals x squared. It's not surjective. It misses everything below the x-axis. It's not injective because we have multiple inputs which give us the same y value. All right. In fact, any sort of parabola is going to do this. Or we could have done the sine function, right? Let's say we do our sine function. Right? Go both directions. Yeah, of course it's not injective because it keeps repeating values. It's not surjective because, well, it never gets above 1 or below -1, right? So lots and lots of options for this one. All right, so that's problem 3. All right, let's move on to problem 4. Problem 4 asks, what is the difference between the codomain of a function and the range of a function? Okay, so this gives people fits sometimes. So let's say I have a function f with domain S and codomain T. Okay, so S here would be the domain, T would be the codomain. Okay, the codomain is a set which contains all of the possible values of f. Okay, so the codomain of f is a set in which all images of f are elements. Okay, but now the range, this sits inside the codomain as a subset. So the range of f or which we could write as, in this case, f of s, is the set containing exactly the images of f. Okay, so as an example, I could write down the function f from the real numbers to the real numbers, which sends an element x to x squared. The codomain of f, well, we just see it here. It's the real numbers, because every square is a real number. So the codomain of f equals r. However, we know that when we graph y equals x squared, or in this case f, right? F of x, we know this is a parabola. And the only values that we actually get are the ones between 0 and infinity. So the range of f, in this case, equals the closed interval 0 to infinity. Okay? So the range is the actual values we reach. The codomain is the potential values that we can get. Okay, let's move on to problem 5. Okay, so in problem 5, that's actually a really straightforward problem. We're just asking what result tells us that if I have two real numbers a and b, then the absolute value of their sum is bounded by the sum of their absolute values. So, of course, this is called the triangle inequality. Okay, well, that's easy enough. All right. Now I anticipate a couple of people are going to write down maybe a variation of this. Namely, they might say, well, what if you took the difference in the absolute values of a and b and then looked at how far apart those are? That difference is bounded by the difference between a and b. And this is what we call the reverse triangle inequality. So every once in a while, people will confuse these two. Okay, but typically the one with the addition is what we call the triangle inequality. The one with the subtraction is the reverse triangle inequality. Moving on to problem 6, we are asked to identify which one is in bold, of the following statements is false. Give an explicit example to justify why that statement is false. Okay. Let's see. Each statement we can assume A, B, C, and D are all real numbers. Fine. Well, this first statement, that actually looks a lot like the reverse triangle inequality that we just mentioned. The only thing missing is, over here there were absolute values on the outside, and down here there are not. But that actually tells us if I take the difference in the absolute values, well, that is certainly bounded by the absolute value of their difference, right? Any number is bounded by its absolute value. But then by the reverse triangle inequality, this is bounded by the absolute value of the difference of a and b. So this is a true statement. This next one, let's see, if a and b are within d of each other, then a is in the b coin of radius d. That's how we could state this. Okay, so let's put b down here. We put b plus d. We have b minus d. So this has a distance of d there, distance of d there. Well, if you are within d of b, right, and that's what this says, a and b are within d of each other, then you're in this coin. So in fact, this is a true statement, right? A's got to live somewhere within d a part of b. So there we go. The next one, if a is at least b, then a times d is at least b times d. Well, that seems right. In fact, we even have a theorem that looks just like that, except there's this one little problem, right? If we read this sort of conceptually, we're saying if a is at least b, then multiplying both sides by d does not change the direction of the inequality. And that's actually something we know is false. If we multiply by a negative number, then we can potentially change the direction of an inequality. So as an example, so this is going to be false, and as an example, I know that 5 is at least 3. And if I multiply by -1, well, I get -5. And if I multiply 3 by -1, I get -3. But -3 is actually greater than or equal, well, I mean, of course, in all these cases, it's not equal, right? Greater than -5. So the inequality has reverse directions. So C is false. D saying, well, it looks like the same thing. If A is at least B, then adding D to both sides doesn't change the direction. And that's actually a theorem that we have. So that's a true statement. All right, let's move on to problem number 7. Okay, so for problem number 7, we're given a bounded subset of the real numbers, and we simply want to define the supremum and the infimum of D. All right, so this is pretty simple. The supremum of D is going to be, well, the supremum looks at upper bounds of D, and of all the upper bounds, it wants the smallest one. So this is the least upper bound of D, which actually makes sense here because D is a bounded set, so it does have an upper bound. We pick the smallest one. Okay, now maybe you might say, well, how do you know there is a smallest one? And of course, this gets to something we'll get in a future problem. The infimum of D, well, this is going on the other side. You're looking at lower bounds, and of all the lower bounds, we want the greatest lower bound of D. Okay, let's say we wanted a little more detail. What do you mean by an upper bound of D, right? So, and specifically a least upper bound. All right, so let's make this even clearer. So let's go maybe give a short name for this. Maybe we'll call it little s. Okay, is a least upper bound of D if for all x in D, s is greater than or equal to x. So that tells you that it's an upper bound, right? It's bigger than everything in D, or at least as big as everything in D. And, well, now we need the least part, right? We have the upper bound, now we need the least part. If t is some real number, such that t is at least x for all x in D. So if we have another upper bound, then, well, we want s to be the least upper bound, so s should be less than or equal to t. Okay, so this is a long form version of this. Of course, the infimum we are going to write down more or less the same way, so maybe I'll call this little l. And this is going to be a greatest lower bound of D or for D. If for all x in D, well, now we want L to be less than or equal to x. That gives us the lower bound portion. And if T is some other lower bound, so T is less than or equal to x for all x in D, then, well, now we want little l to be the greatest of the lower bounds, so little l should be greater than or equal to T. All right, so that's our definition. All right, well, let's move on to problem 8. In problem 8, we're asked now to use our understanding of what the supremum and infimum are to actually find the sup and inf of a specific set D. So let's maybe sketch this set D, right? It's a union of, well, a couple of intervals as well as a singleton set. And that might help us here. So let's see, the first one, we go from 1 to 3. So there's 1, and let's say there's 3, and we don't include 1, but we do include 3. So we get this here. Okay, then we're taking the union, so we get to include more stuff between 2 and 6. Okay, well, 2 is going to be here. We already have all that stuff up through 6, and we don't include 6. So we're actually now getting everything between 1 and 6, but not including 6. And then we union with this one extra point, the point 9. All right, so we'll put that right there. Okay, so we just get this one extra point. So when I go to compute the supremum of D, I need the supremum to be the least of all the upper bounds. Okay, now if it wasn't for this 0.9, I would say that 6 was the least upper bound. Right? It's certainly bigger than all the rest of this yellow, and there's nothing smaller than it, which is bigger than all the rest of the yellow. But then there's this 0.9. So 9 is definitely in the set, and so that's actually going to be my supremum. Why? Well, okay, it is an upper bound. 9 is at least as big as all the yellow points. Also, there's no smaller point, which is at least as big as all the yellow points, because, well, 9's in that set. All right, now what about the infimum? So the infimum of D, well, now that has to be the greatest of all the lower bounds. So I look to the left and I say, well, everything in this set is at least as big as 1. So 1 is a lower bound. On the other hand, if I take anything bigger than 1, then there will be stuff smaller than it that's in this set. All right, if I chose some point over here, look, there's some yellow to the left of it. So the infimum is going to be 1. All right, let's move on to problem number 9. Okay, so here in problem 9, we're given, again, a bounded subset of the real numbers, and we're asked, how do we know that the supremum and the infimum exist? And the answer is, quite simply, this is the axiom of completeness. Now, strictly speaking, when we wrote down the axiom of completeness, we only stated it in terms of the supremum. We said if you had an upper bounded set, then it has a supremum. Okay, there will be a least of all the upper bounds. But we could then turn around and show that given that that was true, that any lower bounded set was going to have an infimum. And the argument was, simply you just, okay, take an upper bound or a lower bounded set rather, negate everything, and now you have an upper bounded set. It will have a supremum, now unnegate, and that supremum becomes an infimum. All right. Well, that was fast. Let's move on to problem 10. Okay, so in problem 10, we're asked to state the nested interval property. Okay, this isn't so bad. So what the nested interval property talks about is, well, hey, nested intervals. So if we have intervals here, of course, they're going to be specific types. They're going to be closed intervals. So if I have a sequence of nested closed intervals, okay, so is we'll say a decreasing sequence. Okay, decreasing is talking about this subset containment. Okay, so they could be equality though, is a decreasing sequence of closed intervals. So each interval is getting, is the same as the previous one or is getting strictly smaller in the sense that it is a subset of. Okay, then if I take the intersection of all of these intervals, there is some element that still remains. So any intersection of a decreasing sequence of closed intervals is non-empty. And that's the nested interval property. Okay, on to number 11. Okay, so in problem 11, we're asked to classify, looks like 6 different sets as being finite, which maybe we'll, let's see, write that as F, countably infinite, so how about CI, or uncountably infinite, so we'll use UI there. Hey, we don't even have to justify our classifications. Great. So we've seen a lot of these things before. So for example, Q, this is the rational numbers. This is maybe surprisingly a countably infinite set. So we had this nice argument that showed we actually could put the rational numbers into a bijection with the positive integers. Okay, then we have the positive real numbers. So, well, we know the real numbers are uncountable, and getting rid of roughly half of them really doesn't help our cause much if we're trying to make it smaller. The positive real numbers using, for example, a variation of a diagonalization argument or doing a bijection between the reals and say the interval 0 to 1 will show us that is uncountably infinite. Okay, the next one, the set of real numbers between 0 and 3. Well, this is, right, whether you're talking about the open interval 0 to 3 or the closed, right? It's not even specified here which, because it doesn't matter. Whether you include the extra points on the ends is irrelevant. In either case, this is still an uncountably infinite set. These are in bijection with the interval 0, 1, which we proved directly was uncountably infinite. Okay, you can just divide each of the elements in here by 3. You'll end up in the set 0 to 1. Okay, the next one, the set of real numbers whose squares are negative. Oh, the squares are negative. Well, wait a second. When I square a real number, I always get something non-negative. So in fact, this is the empty set. Okay, this is the empty set, and the empty set is finite. Okay, next one. The set A, which is, okay, it's a union of, okay, sets AN. Well, what's AN? Each AN is countably infinite. So I have a union of countably infinite sets. Okay, and it's actually an infinite union of them. Cool. Well, we actually had a result as part of our countability omnibus lemma, said if you take the union of countably infinite sets, okay, a countable union of the countably infinite sets, which this is because we're counting by n, it is still countably infinite. And finally, we have the set of irrational numbers. Well, recall the real numbers are the disjoint union of the rational numbers and the irrational numbers, denoted here by I. Well, we know again that the union of countably infinite sets is countably infinite, and Q is countably infinite. So if the irrationals were also countably infinite, if this was the case, then we would know that R was countably infinite. But that's silly. We know the real numbers are uncountably infinite. And so we conclude the irrationals cannot be countably infinite. They must be uncountably infinite. All right, there we go. On to number 12, where we'll talk more about this in the context of Cantor's diagonalization argument. All right, so in problem 12, we're talking about Cantor's diagonalization argument. And says that one assumes, for the sake of a contradiction, that the set 0, 1 can be written out as a list. So let's recall what you would do is you say, okay, we put all the numbers from 0 to 1 in order. And so maybe one of them looks like, 0.348627, etc. And then the next one, right, this is number 1. Number 2 is going to look like 0.50716992, ... And then the third one looks like 0.867539, ... And we keep going. All right, maybe we'll do one more here. 0.00012334, ... etc. And we make this list. It goes on forever. Okay, fine. One then produces an element of 0, 1 that is not on the list, right? We claimed every real number between 0 and 1 is on the list, and yet we're going to build a number which is not on the list. So we build this number x, and what can we do? Well, we look at this first digit. We say that's a 3. Okay, and so I'm going to turn it into a 5, say. So I have 0.5. And then I look at the next digit, the second one, but from the second entry. Okay, and that's a 0, which is also not equal to 5. So I'm going to make this a 5 also. And then I'm going to go to the third line and look at the third digit, which is also not 5. So I'm going to turn it into a 5. Okay, and I go to the fourth digit here, and that's also not 5, so I turn it into a 5. Unless you think that I'm always going to be getting a 5, well, let's write down another one. So this is going to be 0.000531, ... And now I go to this fifth position in line 5, and it is a 5, so I'm going to turn that into a 6. Okay? And I keep going this way. If it is a 5, I turn it into a 6. If it's not a 5, I make it into a 5. And the idea is that this, if I keep going, cannot be in the list. Why not? Well, if it was in the list, then it would have to show up somewhere, right? Maybe it shows up in the nth entry. But what does the nth entry look like? Well, it's going to be 0 point stuff, okay? So there'll be like a first digit and a second digit and so forth. And then at some point you'll have the nth digit, and it'll keep going from there. But this is the one that we care about. If that nth digit is a 5, then in x, when I get to the nth digit, I'm going to put a number which is either 5 if this is not a 5, and 6 if this is a 5, which means they're not going to be the same in the nth digit, right? So this is either a 5 or a 6, I'm not sure which, but if an is 5, then this digit will give me a 6. If an is 6, then, or not 5, I should say, this is not 5, then I make it into a 5. So even though I'm claiming x is supposed to be the nth digit on the list, it's not the nth digit because it differs in the nth place. Okay, and so what is this question then saying? This seems all fine and good. All right, Cantor's diagonalization argument shows the reals are not countable. Explain why this argument fails to show that if I only look at the rational numbers between 0 and 1, that set is uncountable, right? Well, what's going wrong here? If I take all of the rational numbers between 0 and 1, and I say, okay, well, let's put them all into a list, can't I make this exact same argument? And the answer is, well, you can, except for one little detail. The detail is this. I can write down all the rationals between 0 and 1. I can build an x using the exact same rules. Nothing changes there. However, at the end of the day, in the original argument, we said, I have a real number, x. X is a real number, which is not in the list, right? X is not in the list. If I put only rational numbers into this list, and I build this x, it is still the case that x is a real number, but x may not be rational. So this might not be rational, which means I have not found a contradiction because I did not find a rational number not on the list. Okay, so this is the reason, okay? Cantor's diagonalization argument produces, so we'll abbreviate it, CDA, Cantor's diagonalization argument, produces an element not in the list that may not be rational. And if it's not rational, then what have we done? We haven't made a contradiction because the contradiction is that, I found a rational number not on the list. But if CDA produces something that's not rational, you haven't done anything. Okay, so that's how we do number 12. All right, we'll see you in problem 13 in just a moment.
Okay, so let's take a look at problem 13 then. In this problem A, it's just a definition problem. We're given a sequence A of real numbers, L is some real number, and we want to use either the language of coins or this epsilon, n of epsilon language to define what it means for the limit of A dot to equal L. So let's actually use both languages. Okay? So the limit A dot is equal to L if every L coin contains a tail of A dot. Okay, so remember what this is meaning. I draw a real number line. There's some L. I draw an L coin, so this looks like L plus epsilon, and on the left we have L minus epsilon. And the idea is that, well, maybe not every term in the sequence lies within epsilon of L, but once I hit some tail, so remember we denote a tail by something like A greater than or equal to n. So this means that if I have little n at least as big as big N, so if this is true, then A little n should lie inside this coin. So L minus epsilon to L plus epsilon. Okay, so there's our first definition, that every L coin contains a tail of A. The second version, using the epsilon, n of epsilon language, which you can actually almost see it right here, we typically say if for all epsilon greater than 0, there exists some positive integer, n of epsilon, such that if little n is at least as big as n of epsilon, then the distance between a sub n and L is less than epsilon. Okay, or alternatively, you could even write a sub n is in the L coin of radius epsilon. That would be fine too, but this version up above is more standard. Okay, let's move along to problem 14 so we can look at some limits of actual sequences. All right, so let's check out problem 14. It looks like we have 3 different sequences, and we want to know if their limits exist, and if so, what they are. And if they don't exist, then we're going to try to figure out why they don't exist. So let's look at the first one. So we actually have here a difference, essentially, of 2 sequences. The sequence 3 over n and the sequence n squared plus 1 over 5n squared minus 6. So if we can deduce that each of these individual limits exists, then the limit for b dot will exist, and it'll just be the difference of the limits of the 2 individual sequences. So let's take a look at those individually. So the sequence 3 over n, well, we've seen this several times before in the class. As n goes to infinity, 3 over n goes to 0, so that part exists. All right, how about the more complicated looking part? So this is n squared plus 1 over 5n squared minus 6. So you may recall a little rule we talked about, which is if the numerator and denominator of a rational function, when we're talking about a sequence here, have the same degree, then all you have to do is look at the coefficients of that highest degree, and that ratio of the coefficients will actually be the limit. Okay, so we should suspect this goes to 1/5. Now, if you don't see why that's true, right, we can break down the algebra a little bit. So let me take n squared plus 1 over 5n squared minus 6. And let me factor in n squared out of, well, just everything I see. So I have n squared times 1 plus 1 over n squared. Okay, distribute back, you see I get the same thing. N squared times 1 is n squared times 1 over n squared is 1. And then on the bottom, I factor again that n squared out, and I'm left with 5 minus 6 over n squared. And now, because n is going to infinity, I don't have to worry about n being 0 here. I can cancel the n squareds. I get 1 plus 1 over n squared over 5 minus 6 over n squared. And I now have 4 different sequences at play. I have the constant sequence 1, which certainly converges to 1. I have 1 over n squared, which converges to 0. I have 5, which is constant, converges to 5. And I have 6 over n squared, which also converges to 0. In fact, 1 over n squared converges to 0. Multiply it by 6, there's a nice limit property. Doesn't matter, 6 times 0 is 0. So in total, each of these individual sequences converge, and so the sum and their ratios are going to converge. And it'll converge to, let's see, 1 plus 0 is 1, over 5 minus 0 is 5. Hey, wait a second, that's what we claimed over here. Beautiful. So in total, the individual sequences converge, and hence their difference converges to 0 minus 1 over 5, or negative 1/5. Cool. All right, let's check out C. C dot, where, so this is, remember, our notation for the tail of C that starts in the 5th term, right? So it's C5, C6, etc. And we know that the tail converges to 12. But this gets back to our whole understanding, right, of sequences versus their tails. If we're talking about convergence, we really only care what happens in a tail, right? In fact, our definition for a limit, we talked about, every L coin contains a tail of the sequence. And so, as soon as we know that a tail converges to 12, then actually the entire sequence has to converge to 12. So this implies that C dot converges to 12, since tails detect convergence. Okay, this is one of our theorems. All right, finally we have sequence D, where a subsequence dn dot converges to 0. Now, we know that subsequences inherit convergence, meaning if we know that D converges to something, then any subsequence will also have to converge to that exact same value. So if D converges to anything, it would have to be 0. But it doesn't have to converge to anything. In fact, we could write down, so this one we claim we don't know. Okay, so it's not possible to conclude that D converges. Since, well, let's do an example. D could equal, okay, well, let's see. What if I do 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, etc. There is a subsequence, namely just take the odd indexed terms, that converges to 0, right? So D and dot would just equal 0, 0, 0, 0, so forth. And that definitely converges to 0. But D dot does not converge to 0. D dot diverges. Because it's going back and forth between 0 and some steadily increasing natural number. All right, so no way to know what D converges to. In fact, it may not converge at all. All right, on to problem 15.
All right, so in problem 15, we're given a list of, my goodness, 7 different statements, and we want to figure out which of these is the monotone convergence theorem and which is the Bolzano-Weierstrass theorem. Well, let's take a peek at these things and see what we can say. So first, every bounded sequence converges. Well, that's just not true, right? For example, we have 1, -1, 1, -1, etc. That's a bounded sequence, never gets above 1, below -1, but it definitely doesn't converge. So nope, that's not it. Let's see. Every bounded sequence is monotone. Well, no, right? Like we just saw one. This exact same sequence is bounded, and it's not monotone. It's going up, it goes down, it goes up, it goes down. Okay, so nope, it's not that one. Every monotone sequence is bounded. Oh, well, that's easy to break. 1, 2, 3, 4, 5, etc. Okay, this is not a true statement. Whew, okay, so 3 false statements. No chance these were the monotone convergence theorem or the Bolzano-Weierstrass theorem. Okay, let's look at D. Every bounded sequence has a convergent subsequence. Oh, and that one sounds familiar. In fact, that right there is the Bolzano-Weierstrass theorem. You have a bounded sequence, we automatically know there is some subsequence that converges. Okay, let's look at the next one. Every monotone sequence has a bounded subsequence. Every monotone sequence has a bounded subsequence. Well, you know, actually the same one from up above just disproves that. 1, 2, 3, 4, 5, etc. This is a monotone sequence, and there's no subsequence of it that's bounded, right? You take any subsequence, it's always going to be increasing to infinity. So E, definitely not going to work. F, every monotone and bounded sequence converges. Once you combine both monotone and bounded, that actually tells you of convergence. That is the monotone convergence theorem. Okay, so D and F are the solutions. D for the Bolzano-Weierstrass, F for monotone convergence theorem. And let's just take a quick peek at G. Every bounded sequence has a monotone subsequence. Ooh, now that's an interesting one. In fact, while I'm not going to prove it here, this statement is actually true. And in fact, this statement doesn't even rely on the word bounded. So if I remove the word bounded, every sequence has a monotone subsequence. This is actually a true statement. Okay, but for this problem, we just need to identify MCT and BWT. All right, let's check out problem number 16. In problem 16, we're simply doing a definition here of a Cauchy sequence. And let's see, they've even given us the first part of it. So a sequence A of real numbers is Cauchy if for all epsilon greater than 0, there exists n of epsilon such that if m and n, so little n, are at least as big as n of epsilon. Okay, so we go out past n of epsilon, so we're in a tail. Then the distance between am and a sub n is less than epsilon. So that's all Cauchy is getting at. Remember, the reason we have Cauchy sequence to begin with is we may have some sequence that we suspect converges, but to what we may not be sure. So instead of trying to compare the sequence to some fixed real number that we don't know exists, instead we compare the sequence to itself. And we ask, do the terms of the sequence, at least in a tail, get close to each other? Always close to each other. So, meaning if I go out past n of epsilon, are all the terms of A within epsilon of each other? Okay, on to problem 17. Okay, so in problem 17, we're given 4 statements, and we're asked to determine which of them is false. And for those that are false, we're going to have to give some sort of an example to justify that claim that they're false. So let's see, the first one, every sum sequence converges. So this is just brutally false, right? This is just terribly false. So an easy example is we could take the sum sequence, right? Looks like 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1, right, etc. Okay, corresponding to the sequence, right? So I can have here A just being the constant sequence 1, and so forth. And so then this would be the sum sequence for A, and this just blows up, right? So this diverges to infinity. Okay, so that one's definitely false. Let's see, second one. If a sequence converges to 0, then the corresponding sum sequence converges. Yeah, okay, so this one is more subtly false, but we have a great example here. So if we take the harmonic sequence, given by 1, 1/2, 1/3, 1/4, etc., then we know that the harmonic series, right, or harmonic sum sequence, which is right, given by 1, 1 plus a half, 1 plus a half plus a third, etc. Even though, right, this h converges to 0, this sum sequence corresponding to it, again, diverges to infinity. Okay, this was a bit of a surprise, maybe. Okay, 17c. Okay, so yeah, so this one is false, right? 17c, if r is a real number, so any real number, then, this looks like a geometric series, right? So, then this geometric series equals 1 over 1 minus r. Yeah, this is tricky because there is this formula that would tell you that's what it equals. But this is false. Again, because there's actually a hypothesis, right? We always have to check the hypothesis. What would make this statement true is if the absolute value of r was less than 1. If we make r not between -1 and 1, we have a problem. So we, for example, could consider r equals 1. Then we would have this sum of 1 to the k, which is the sum just of 1, and this diverges, right? Just add up an infinite number of 1, and again, it diverges to infinity. All right, so the first 3 of them are false. Let's see if there's any truth in this whole problem. The last one, if we have a sum sequence that converges to k and a subsequence b that converges to L, then the sum sequence corresponding to the sum is equal to the sum of the limits. Actually, that's a true statement, right? That actually comes from one of our algebraic convergence theorems for sum sequences. Okay, so this is true by the algebraic, I can't remember what we called these things. Let's call them a limit theorem for series, say, right? Or for sum sequences. Okay, so there we go. 3 falses and a true. All right, let's check out problem 18. Okay, so problem 18 asks us to give an example of an open subset of the reals that is not an interval. So what did it mean to be an open subset? Well, O, a subset of the reals, is open if every point in O is an interior point. Okay, which of course, interior points are automatically points in O, so this would mean that O is equal to the set of its interior points. Okay, fine. Intervals are a fantastic way of making sure that everything in your set is an interior point. So if I draw an interval, and I choose any point in this interval, then I'm able to put a coin around it that stays inside the interval, no matter how close I get to this wall. And that's why it's important here that I use the parentheses. If I had the square brackets, well, then I would get these endpoints included. And if I chose a point on the end, now it's not possible to put any sort of a coin around it that is entirely inside the interval. So this over here is open, this is not open. Okay, but we don't want to have an interval here, right? We want an open subset which isn't just an interval. In the real numbers, it turns out that, well, intervals kind of make up all of the open subsets. So the easiest way to do this would be, for example, what if we took an interval and then another interval? And then I take the union. This is not an interval anymore. It's a union of two intervals, but they're separated. So this is not a single interval, but it's still an open subset. We know that the union of open subsets is an open subset. So the union of two intervals, open intervals, will be an open subset. Now, while it wasn't required for this problem, I think it's kind of fun here to actually write down a much stronger result, which is to say that if you were going to write down a solution to this problem, that is some open subset of R that's not just one single interval, then you actually had to answer in a way similar to the example I gave, right? So here's a theorem, which is every open subset, well, let's say non-empty, all right? We don't want to worry about the empty set, but every non-empty open subset of the reals is a, well, I want to say a union of open intervals. But in fact, I can even restrict it to how many. So I can't necessarily use a finite number, right? That may not be possible. And you can easily write down examples, like I could, for example, do 0, 1, union 2, 3, union 4, 5, union 6, 7, and then I just keep on going forever and ever. This is an open set. It's a union of open intervals, and we know that any union of open sets is open. And so this definitely could be infinite, but I could even, I could maybe say, well, what if I could come up with some union that used an uncountable number of these things, right? So here's one where I've certainly used a countable number. But it turns out you don't have to worry about uncountability. So it will be a countable union of open intervals. And heck, you know what? Why don't we try to give a proof of this? How fun. So let's say I have some open set. So O here is going to be some subset of R, which is open. And let me choose some element in X. Okay. So we take some X, some element in O, right? We'll call it X. So X is going to be some element in the set. Now, because O is an open set, we know that there is an X coin that's contained inside of O. And then, of course, an X coin is an interval. So O contains an interval containing X. Okay, fine. So it contains at least one interval that contains X. But there might be more, right? Well, in fact, once you know there's one, there's infinitely many that are going to contain X. So what I want to do is take the union of all of the intervals that contain X. And if I do so, right, I have to get another interval which contains X and which is somehow the largest, right? Because it contains all of them. So the union of all intervals containing X, which is non-empty because there we go, we know there's at least one. So the union of all intervals containing X, we denote by, well, interval, we'll say I and then say sub X. Okay, and this is, right, the largest interval containing x. Okay. Now, if I have a couple of different elements in my set, so maybe here's my x, and then over here maybe I have some y, and these are both in O. And I say, okay, I can compute I sub x and I can compute I sub y. And let's say I compute my I sub x and it looks something like this. Then I go to compute my I sub y and it looks something like this. And notice there's this overlap here between the I sub x and the I sub y, right? So I have I sub x here and I have my I sub y over here. Well, yeah, doesn't it make sense so then? I could actually combine Ix and Iy and I'd get a longer interval, right? I mean, there's just, it doesn't stop, right? This is an open set. Everything in either both the yellow and the green is contained in O. So I'd get just a bigger interval, but Ix is supposed to be the largest interval that contains X. So what we conclude from this is that if I have two elements X and Y, then I cannot have any overlap between the Ix and the Iy unless maybe the Ix and the Iy are exactly the same thing. Okay, so the way we would say this is that any two of these Ix's and Iys are either disjoint or equal. So that means I can actually kind of break things up. I say, well, I have all these different points X and Y, but a lot of them give you the same largest interval, right? Ix could equal Iy. And the ones that don't are disjoint. So I just take the collection of all of the distinct maximal intervals. Okay, so the collection, and well, since we don't want to use the specific x, okay, we could use some indexing term, right? I think we like to use alpha in class. So the collection, right, of all these of these maximal intervals, right? So of all the distinct maximal intervals containing elements of O, well, that contains every element of O, right? So this collection, okay, is going to contain every element of O, right? So this covers O. Okay, so this implies that O is equal to the union of all of these I sub alphas. Okay, so alpha here would be, well, I don't want to use I for indexing set, so I'm just going to say over all the alphas. We don't know which points we're choosing. Okay, so now I've written my O as a union. In fact, it's a disjoint union, so we use a little dot notation. A disjoint union of open intervals. But I claimed it was a countable union of open intervals. How do I know it's countable? Well, every interval contains a rational number, right? So every interval, doesn't matter which intervals I'm talking about, right? This is the density of the reals here. Every interval contains a rational number. And so in fact, I could choose this index alpha to be some rational number. And so the collection of all these I alphas is going to be indexed by a subset of the rational numbers. Okay, thus this set here, this collection, is indexed by a subset of the rational numbers, so a subset of Q. But Q is countable. All right, Q is countable. Okay, therefore every subset of Q is countable. Okay, and so that's it. We've just shown we can write our O as a union of open intervals, and the number of those open intervals, right? Well, it's infinite typically, but it's a countable infinity because we can index it with a subset of the rationals. Whew, okay, well, we didn't need all that to solve the original problem, but it's kind of good to know that every solution really did have to look like this. All right, let's move on to problem 19. All right, in problem 19, we are given, ooh, wow, an intersection of a whole bunch of sets. This is an infinite intersection. And each of the sets is an interval. And it looks like, yes, it's a 7 coin with radius 1 over n. Well, 7 coins are always open. So, hey, maybe this is going to be open, right? We're doing an intersection of open sets. That's sometimes open, right? Well, let's see. So I have over here 7 minus 1 over n, 7 plus 1 over n. But I notice as n gets larger, then these parentheses are going to move in, right? As n gets larger, 1 over n gets smaller. And so, for example, maybe I double the n here, and I might come in a little bit, and I'd get 7 plus 1 over 2n. And over here, I might have 7 minus 1 over 2n. And so these things are actually going to keep getting closer and closer to the 7. And as I intersect them, I get fewer and fewer points. In fact, I'm not going to be able to get anything in this intersection other than the number 7. You may say, wait, how do you know you don't get anything in there? Well, let's say here's 7 right here, and I think that there's some other point, right? So maybe this is the other point which is going to be in the intersection. However, I know I can make an n large enough, this is by the axiom of Archimedes, I can make an n large enough that this interval will stop before I get to this 7 plus something. So maybe this was 7 plus some epsilon. I know that there is some 1 over n, which is less than epsilon. And so this could be 7 plus 1 over n. And now this 7 plus epsilon dot, that's not going to be in the intersection. So in fact, if I take the intersection of all of these open intervals, I simply get a single point set, right? Sometimes called a singleton set, set 7. Is this open? Oh boy, no. An open set has the property that all of its points are interior points. That doesn't mean it's in the set, right? 7 yes, it's in the set. That's not the issue. Is it an interior point, meaning does the set contain a 7 coin? Well, no, it only contains the number 7. Any 7 coin will contain more. So definitely not open. Well, that means if it's not open, it's not both. So it's either closed or it's neither. Well, we know that a singleton set is closed, so this is actually going to be the correct answer. And why is it that it's closed? Well, to be closed, all of your points have to be boundary points. Well, what does it mean to be a boundary point? Right? Is 7 a boundary point of the set containing 7? Well, to be a boundary point, anytime you put or look at a 7 coin, it has to contain points that are both inside the set. Well, sure, every 7 coin contains 7. That's inside the set. As well as containing some point outside the set. And yes, absolutely, if I write down any 7 coin, it's going to contain something not equal to 7. So in fact, yes, 7 is a boundary point, and it's the only boundary point. Therefore, the set containing 7 contains all of its boundary points, and thus is closed. So we don't get neither either. All right, let's move on to problem 20. In problem 20, we are given 5 different examples or descriptions of subsets of the real numbers, and we want to know which of them are compact. So let's see, the first one, we have a subset that's the intersection of closed and bounded subsets. Well, we actually know that closed and bounded is one characterization, in fact, it's our definition in the real numbers for compact sets. So we're asking, is the intersection of compact sets compact? Of course, the answer is yes. The intersection of closed sets is closed. The intersection of bounded sets is bounded. Therefore, we have compactness. Second one, the continuous image of a compact subset of the real numbers. So you may recall we worked examples where we took the continuous image of an open set and got something not open. We took the continuous image of a closed set and got something not closed. However, the compact description, yep, that is preserved by continuous images. And so in fact, continuous image of a compact subset is compact. All right, the third one, a subset of R for which every open cover has a finite subcover. This was our topological characterization of compactness. So in fact, this subset is also compact. Next, we have a subset of the reals for which every sequence has a subsequence that converges to an element of the subset. Yep, that is our sequential characterization of compactness in the real numbers. So this is also compact. Okay, so our last one gives us a specific union of intervals. So let's draw a picture. Make sure we don't get this one wrong. So first, we have 5 to 9. So let me start at 5, and we'll go all the way to 9. We don't include the endpoint 9. Then we're going to take a union of 7. Okay, so maybe that'll start, like about there. And we go all the way to 10, and we get to include the endpoint. Now, since we're taking the union of these two, we get everything that's in either one of them. And so, in fact, this is just the closed interval, 5 to 10. Well, it's closed, it's bounded. Hey, it's compact. So, in fact, every single one of these subsets of the real numbers is compact. Okay, let's check out problem 21. In problem 21, we're given a function from some domain D to the reals. We're given a limit point of D, call it A, and there's some real number L. And we want to know which of the following three statements implies that the A limit of F is equal to L. Cool, so let's see the first one. Every L coin contains F of A. Well, let's draw the picture. So I have D, I have the real numbers, there's some A, and there's some L. And it says every L coin, okay, fine, I'll draw an L coin, is supposed to contain F of A. So that means I apply F at the point A, and it has to be somewhere in there, no matter which, all right, so this would go to like here, no matter which coin that I choose, it would have to go in there. Well, that's an interesting thing, except there's some very serious problems with that. First, we know that A is a limit point of D. We don't even know that A is in D, right? Being a limit point, well, it might be on the boundary, for example. So we don't know that A is in there, so which means that F of A may not even make sense. Second, when we compute a limit, the idea is we're looking at points X that are close to A, but not equal to A. So this has nothing really to do with the limit definition. So nope, not 21A. All right, 21B. For every D not equal to A sequence that converges to A, and we'll put a little hyphen in there, for every sequence, right, which is in D but doesn't have points equal to A that converges to A, we have F of A converges to L. So this is exactly what we called our sequential characterization of functional limits. So this absolutely works, right? This is the sequential characterization of functional limits. Okay, how about C? For all epsilon greater than 0, there exists a delta greater than 0 such that f of x minus f of a absolute value is less than epsilon. Well, this is supposed to make you believe this is the standard definition of the a limit of f. But something should concern you here. You'll notice there exists delta greater than 0 such that, and then this next piece has nothing to do with delta. Right? The point is, when I choose an L coin, okay, say of radius epsilon, then I need to find some delta, which is going to be the radius of a punctured A coin. So this would be A plus delta, A minus delta, and then we ignore the value at A. We actually don't even care what F does at the point A, right? So we don't need any of that in there. Instead, we're only interested in what happens inside this punctured A coin, where we remove A from consideration. Okay, so if we had added in such that if X is in D and X and A are within delta but not equal to each other, then we would have that the distance between f of x and f of a is less than epsilon, meaning the f image of x is in the a coin, or the f of a coin rather, of radius epsilon. Oh yeah, there's this other little thing here, right? This says f of a. It should say L too, right? Like that was really the goal, is we want to get close to L. F of a again may not exist. So there's just all sorts of things going wrong here, right? Meant to try to confuse you, but this is actually, right, a common mistake that students are making. Okay, we'll see you in problem 22. All right, so in problem 22, we have the return of Clever Carl. Clever Carl says that if you have two functions with a common domain D, codomain R, and some limit point A, then the limit of a sum is equal to the sum of the limits. Okay, that seems familiar. He then wonders what would happen if f of x was equal to x and g of x was equal to negative x. Of course, he says f of x plus g of x is equal to 0, and so the limit of the sum is equal to 0. Okay. Right. What would happen if he took the limit as x went to a of f of x? Well, okay, it would go to, I guess, a. And for g of x, I would go to negative a. A plus negative a is 0. This, oh my gosh, is Carl actually correct for once? Well, no. As we said on day one, Carl will never be correct. It turns out his example is correct. All right, this is in the same way that if I made the claim that the difference of any two positive integers is positive. Well, this is assuredly a bad claim, but look, I do an example. 5 minus 3. Hey, that's 2. That's positive. And 8 minus 1. That's 7. That's positive. Hey, look at that. See, I'm right. Except I'm not, because, of course, I could take any one of these, turn them around, and now I'd have negatives. Well, Carl has the same issue. He has found an example which is correct. However, his claim, namely that the limit of a sum is the sum of the limits, is not correct without further hypotheses. Namely, we need to know that these two individual limits exist. So as an example, if I let my f of x be 1 over x and my g of x to be negative 1 over x, then 0 is certainly a limit point of the domain, right? So, well, let me write here the domain. So the domain could be, say, all real numbers except for 0, right? We don't want to put 0 into these fractions, but 0 is a limit point of the domain. Okay, and so now what happens if I take the limit as x goes to 0 of f of x plus g of x? Well, f of x plus g of x, that's 1 over x plus negative 1 over x, which is 0. And the limit as x goes to 0 of 0 is equal to 0. On the other hand, the limit as x goes to 0 of f of x plus the limit as x goes to 0 of g of x, well, this doesn't exist. Because as x goes to 0, f of x blows up to infinity or down to minus infinity, depending on which side you go to 0 from. So neither of these exist. And so their sum certainly doesn't exist. So Carl once again is wrong, even though he was able to find an example where he was right. All right, let's move on to problem 23. Okay, so in problem 23, we are given 6 different possible characterizations of continuity, and we want to know which ones actually are correct. So in this problem, f is going to be some function with domain D and codomain R. A is some element of D. All right, let's check them off one by one. So first, f is continuous at A if and only if every D coin contains the f image of A. Well, we don't even know what a D coin is. D is the domain of the function, right? So there's no such thing, right, as a D coin here. So yeah, this one just doesn't make any sense. Okay, part B here. So f is continuous at A if and only if D contains a limit point of A. Well, that's not enough for continuity. In fact, you notice this second half has nothing to do with the function f, right? So a could be a limit point of D. But even it contains a limit point of a. I mean, a is not a sequence. A is not a set. Like, there's no, this doesn't mean anything. This is silly. Okay, C, f is continuous at a, if and only if the f image, ooh, that sounds good, it has to do with f, of every D sequence that converges to a converges to f of a. Now that sounds like a characterization of continuity. In fact, this is what we called the sequential characterization of continuity. Okay, so this is our sequential characterization of continuity. Sweet, we found one. Okay, let's go on to D. F is continuous. Oh, on D, so on the entire domain D, if and only if for all epsilon greater than 0, there exists a delta greater than 0, such that if x and y are in D, such that x minus y absolute value is less than delta, then f of x minus f of y in absolute values is less than epsilon. So if we can get x and y close enough, then f of x and f of y are close enough, and x and y are anything in D. Yeah, that'll definitely imply continuity. In fact, it's a little too strong, just a little too strong to be continuity. In fact, this is our condition for the function being uniformly continuous on D. So in one direction, this statement is true, but in the other direction, it's not. Continuity does not imply this condition, so it's not if and only if. Okay, the next one. F is continuous at A. If every f of A coin contains the f image of the intersection of D and an A coin. And that's actually correct too. That was our original definition of continuity. If we drew a picture, we say, okay, there's D, there's the real numbers. I have some point A, and I want to know if f is continuous. Well, it's in the domain, so I can apply f to it, and I get f of A. And it says, okay, we check every f of A coin. So I put a coin around it, and I want to know if this coin contains the f image of the intersection of D and an A coin. So if I find an A coin, now some of these points in the interval may not be in D, but I don't care about those. I only care about the ones that are in D, and I map them, and they all have to end up in this f of A coin. Yep, that's exactly what continuity is. Notice it's not even a punctured A coin or anything. So we have found a third correct characterization. Okay, let's go to the last one. F is continuous, okay, again, on D. If D is open, okay, and if every pre-image of an open subset of the reals is open. This actually sounds a lot like the topological characterization that we gave for continuity. In fact, we showed that a function was continuous on D if and only if the pre-image of every open subset of the reals was an open set, provided that the original set was open. So in fact, this is our topological characterization. And so it is another correct characterization of continuity. So there's 4 in this problem. Okay, let's check out problem 24. Okay, so in problem 24, we're asked to give an example of a function that is continuous except at its boundary points. Ensure that our function has at least 4 boundary points. Okay, well, let's see. If I want to build something with 4 boundary points, well, what if I build some closed intervals, right? So I could do like 0 to 2, and then here we'll jump a little bit, and maybe we'll go from 3 to 4, or 5, right? They look about the same length. Fine. So I want to define maybe a function on here. It has 4 boundary points, 0, 2, 3, and 5. And I want it to be continuous except at those boundary points. So this seems pretty reasonable. What if I just make it jump up to, I don't know, whatever this level is at the endpoints, and then have it jump down to a different level? Okay, and I can do the same thing over here. I'll just copy everything. All right, so it's going to jump down to a different level. So maybe this could be height 1 and this could be height 2. All right, if I want to write this now as a piecewise defined function, I could say f of x. So f is going to be defined from the union of 0, 2, and 3, 5 to the real numbers. And f of x is going to equal, well, it's going to equal 2 if x is 0, 2, 3, or 5. And it's going to equal 1 if x does not equal 0, 2, 3, or 5, right? Or is not an element of this set. Okay, and of course the x has to be in the domain. Okay, and well, of course, there's no issue about continuity when you're away from these boundary points. It's just the constant function. We know the constant function is continuous. But when you get over to the endpoint, oh yeah, there's this big leap here. And so it cannot be continuous there. In fact, we know the value, right, at f of 0, for example, is 2, which means that for any 2 coin, right, so here I could put a little 2 coin, I should be able to get close enough to 0 so that all the values are within that 2 coin. But no matter how close I get to 0, the value is always 1, which is not inside this smaller 2 coin. So this would be an example of a function. It's continuous, except at its 4 boundary points. Okay, well, let's check out problem 25. In problem 25, we're asked to, well, state the algebraic continuity theorem. So we're spotted a couple of things. We have two functions, f and g, with domain D, codomain R. We have some point A and D, and there's some constant alpha in the real numbers. So the most important part of this is, of course, the hypothesis. So let's finish off the algebraic continuity theorem by starting with the important part. If f and g are continuous at A, everything we do afterward depends on this condition. Okay. Now, what are the things? Well, we had these things that kept popping up all over the place. First one is some sort of homogeneity property. If I multiply the function f by the scalar alpha, it remains continuous at A. The second one, let's say I add the two functions f and g together, or multiply the two functions f and g together, either one of these will still be continuous at A. Again, assuming that f and g were to begin with. Finally, if I take the quotient of f and g, this is going to be continuous at A, but only if g of A is non-zero. So this is continuous at A, provided g of A does not equal 0. All right, so there's our algebraic continuity theorem. Okay, let's move on to problem 26. In problem 26, we're given a function f from D to R. Oh, and we're told it's a continuous function. Sweet. And what is the domain? It's this weird union of two closed intervals. Ooh, that's pretty nice, actually. You see, this is a closed interval, this 1, 4, but it's also bounded, which means it's compact. Same thing with this closed interval 6, 7. It's bounded, so it's compact. Now, the union of two closed sets is also a closed set, and of course, this union is clearly bounded. So in fact, we have a compact domain. We have a continuous function on a compact domain. That's fantastic. Whenever you have a continuous function on a compact domain, this immediately implies that the image of f is compact. Fantastic. By the way, just not relevant to this problem, but it also implies that f is even uniformly continuous. All right. Now, part A says, explain how we know that f of d is bounded. Well, we know that the continuous image of a compact domain is compact, and every compact set is bounded. So f of d is compact implies that f of d is bounded. Easy peasy. Okay, part B. Which theorem implies that the supremum of the image of f is actually contained in the image of f? Well, One of the other things we know when we have a continuous function on a compact domain is that a maximal element exists. And which theorem is that? Ah, yes, this is the extreme value theorem. So the extreme value theorem implies that if I look at all elements in D and evaluate f on them, that this maximal element exists. But if the maximal element of a function on a set exists, that means or maximal element of any set exists, then it equals the supremum. Okay, so this exists and equals the supremum. Of course, the supremum is supposed to be the least upper bound, but if you have a maximal element, it is its own least upper bound. And of course, the maximal element, well, this really is in f of d, and therefore the supremum is an element of f of d. So this follows from the extreme value theorem. All right, let's try problem 27. Okay, so in problem 27, we're given a function whose domain is the compact interval 1, 7, and codomain R, and we're told it's a continuous function. And we know that when we put in the input 1, the leftmost endpoint, we get 5, and the rightmost endpoint 7, the output is 12. So if we were going to try to graph this, so okay, there's 1 and there's 7. I know that I got a 5, I've got a 12. There we go. F of 1 is equal to 5. And f of 7 is going to equal 12. And the only other thing I know is that it's continuous. So along the way, stuff is going to happen, but it will happen in some sort of continuous way. Okay, well, what does the intermediate value theorem, right, tell us is going to happen with this function? And what it tells us is that if you choose any point in between, anything you like, there has to be somewhere where I'm actually going to reach that point. Okay? We don't know where, but there'll be somewhere where I actually hit all of these intermediate values between 5 and 12. So if we want to write this out explicitly, we can say for each C in between 5 and 12, there exists some point Z in between 1 and 7 such that f of z is equal to c. Okay, this of course is summarized by saying f satisfies the intermediate value property, but that's exactly the sort of thing I told you not to do, right, when you're answering this question. So this is what we're looking for. All right, let's move it on to problem 28. In problem 28, we are given 4 different statements related to the derivatives of a function, and we want to decide if they're true or false. So let's see the first one. A function needs to be differentiable at a point in order to be continuous at that point. Well, yeah, we've kind of got it backward here, right? So you go to the continuity club, okay, that you need to get in there, and then if you want to be differentiable, well, that's where all the VIPs are, right? So in order to be differentiable, right, in order to get into the VIP section of the continuity club, you first have to get into the continuity club, right? So you have to be continuous in order to be differentiable, not the other way around. Okay, so this first statement is false. Okay, the second one, the derivative at a point A can only exist if the domain contains an A coin. This is actually going to be true. So the derivative is a local property. When we define it, it doesn't make any sense to define it in a vacuum. You can't define the derivative at a single point. You need to define the derivative in terms of points that are near A, and so we insist that we have an A coin in the domain. So this is a true statement. Okay, the third statement, the derivative of a function is continuous on its domain. This is actually false. So it's very possible to build a function which, when you take the derivative, all of a sudden you're going to lose continuity. A classic example of this, which maybe I'll write this down below, is one of our monster functions from class. So if I set f of x to be x squared sine of 1 over x, at least when x is not equal to 0, and then make it 0 when x is equal to 0. Well, we showed in class that f is differentiable, okay, everywhere, even at 0, right? And the derivative is 0. And the derivative is given by, well, okay, at 0, the derivative is just 0. That's no problem. But when I'm away from 0, okay, well, you got to do all sorts of, product rule, chain rule, all that jazz. So I'd get 2x sine of 1 over x, and then, let's see, that'd be minus the cosine of 1 over x. And I guess I'll move this over a bit to the side. Okay, and this is, of course, when x is not equal to 0. The point is that we also showed in class that this function is not continuous at 0. Okay, so this is not continuous at 0, even though it's in the domain. So I take a derivative and I can lose continuity at some points, right? It's sad, but it can happen. So this is a false statement. Okay, finally, 28d, a function is differentiable at a point A with derivative f prime of A, if and only if for every d not equal to A sequence, A dot converging to A, we have that the limit of this difference quotient converges to f prime of A. And this actually looks pretty legit. Yeah, this looks like, what did we call that? Yeah, the sequential characterization of differentiability. Now, when we wrote it down using our DQ notation for difference quotient. But what is this saying, right? I'm looking at applying the difference quotient to f of a dot, which means I compute the difference between f of each a sub n and f of a, divided by the difference between that a sub n and a, and I take the limit as x is approaching a. Oh, it's so close. Oh, it's so close. What is this doing here? That's so rough. Yeah, so everything looked pretty good until we just broke it down piece by piece. And yeah, this x, notice there's no x in here, right? So if we'd wanted to write something, well, I would just cancel this, right? Just not write nothing. But if we wanted to write something, we'd have to write something like n goes to infinity. This is so close. But at the end of the day, this is false. Okay, yeah, that was tricky. I admit it. All right, let's move on to problem 29. All right, problem 29 is a true or false question. We're told f and g are differentiable at A. And, we want to know, is f times g differentiable at A with derivative f prime of A times g prime of A? So we do know that if two functions are differentiable at a point, then their product is differentiable at that same point. So that part is certainly true. But now there's this extra bit at the end here with derivative f prime of A, g prime of A. And of course, this is obviously true, right? Because let's say I let f of x equal the constant function 5 and g of x equal the constant function 8. Then f prime of x would equal 0 and g prime of x would equal 0. And so their product, f prime of x, g prime of x, would equal 0. But of course, if I multiplied fg of x, well, that would just be the product. 5 and 8 would be 40. And fg prime of x is 0. Hey, look at that. Now you might say, well, that's a constant function. That's kind of a strange situation and certainly not the typical one. So we'll try something else. What if we did f of x is equal to e, to the 2x, and g of x is equal to e to the 2x, right? Well, let's see. F prime of x would be 2e to the 2x, and of course that would also be g prime of x. That's fine. Well, what if I multiply? What's fg of x? Well, that would just be e to the 2x times e to the 2x is e to the 4x. Okay, and what is fg prime of x? Well, let's see. That would be 4e to the 4x, and we better do f prime times g prime. So f prime times g prime is 2e to the 2x times 2e to the 2x, which is 4e to the 4x. Hey, they're the same, right? What do you kids say these days? JK? All right. So, yeah, these are a couple of examples where this rule actually does end up working. But in general, of course, no, this is false, right? So there's a whole rule devoted to what happens when you take the derivative of the product. And we know that in general, we should get that fg prime at A is going to equal f of A g prime of A plus f prime of A g of A. Okay, the so-called product rule. Okay, and it just in these two particular situations, we happen to get the right answer despite not using the product rule, but it's more of a coincidence than anything else. Okay, so the answer is false. All right, let's move on to problem 30. Okay, problem 30. Which of the following three statements are true? The first one says we have a function which is defined piecewise, and we claim that because it's defined piecewise, it does not have an antiderivative. And of course, what this is trying to invoke in your mind is the contrapositive form of Darboux's theorem. So Darboux's theorem says that if you have a differentiable function, then its derivative satisfies the intermediate value property. All right, so if I know I have the derivative of a function, then I have to hit every line, right, going across. It doesn't have to be a continuous function, but it does have to satisfy the intermediate value property, right? And what we had learned is if you had some function that has a big jump like so, which usually is coming when we define it piecewise, we know it does not satisfy the intermediate value property on certain intervals, because you don't get, for example, any point on this horizontal line. And then we knew by Darboux's theorem that it couldn't then therefore be a function with an antiderivative. But piecewise doesn't mean that you have such a jump. It could just be you had some function that looks like this, and then the function looks like that. And that satisfies the intermediate value property. So piecewise doesn't rule out, right, that you have an antiderivative. So this one is false. Okay. B, any function that has a maximum has a point where its derivative is 0. So this is trying to make you think of the interior extremum theorem, also known as Fermat's theorem, which is telling you that if you have a differentiable function and you have some maximum, then you know the derivative at that maximum is equal to 0. But this is going the other way around. We're saying if we have any sort of a maximum, right, on any function, okay, we're not talking about a differentiable function. So for example, you could have a maximum that looks like this. And we know that there is no derivative at this max point. Or maybe even you have some function that looks like, I don't know, it's going up, and then there's a little hole, and then it goes way up. That's the maximum. And then it turns around, comes down. Well, there's not even a derivative defined at this max point. And there's no real reason to believe this function has derivative 0. So in fact, the second one is also false. Okay, what about 30C? The derivative of any differentiable function on a closed interval satisfies the intermediate value property. And this is true because this is precisely Darboux's theorem. So we have 1 out of 3 of these things being true. Okay, let's check out problem 31. Problem 31 is another definition question. We're asked to state the mean value theorem and then explain under what circumstances it yields Rolle's theorem as a special case. So let's first do the mean value theorem. So mean value theorem, we're going to start with a function defined on some closed interval AB, and we're going to assume that it's continuous on the entire domain AB, and differentiable except possibly at the endpoints. So differentiable on the open interval AB. Okay, so if this is true, so if f is continuous and differentiable as we described, then there exists some point C between A and B such that the instantaneous rate of change at that point C is precisely equal to the average rate of change of f on the entire interval. So this is the A difference quotient of f at B, or if you prefer, the quotient of f of B minus f of A by B minus A. All right, so there's your mean value theorem. And you recall if we have here A and B, and this is f of B, and this is f of A, then of course the right-hand side, right, this difference quotient is the slope. Okay, slope of line connecting A comma f of A and B comma f of B. Okay, and so we don't know what the graph necessarily looks like, but as long as it's continuous on the closed interval and differentiable on the open interval, then no matter what it's looking like, there's going to be some point where when we compute the derivative, which is the slope of the tangent line, it's going to be the same as the slope of this line connecting, right? So you're going to get parallel lines. The tangent line is going to be parallel to this secant line. Now, in the special case where instead of having this sloped secant line, in the special case where f of A and f of B are the same, that's when we get Rolle's theorem. So Rolle's theorem is same hypotheses plus we assume f of A is equal to f of B. And in this case, the difference quotient will be 0, right? The slope of the tangent line, when we make sure that f of A and f of B are the same, so there can be f of A, there's f of B. Now this has slope 0, and so all we're saying is no matter how you connect these dots together, there's going to be some point where the derivative is parallel to the secant line, or where the tangent line is parallel, and hence the derivative is 0. Okay, and so this will imply there exists some C in AB such that the derivative at C is equal to 0. Okay, that's all it is. All right, let's try problem 32. All right, so in problem 32, at long last, we get to integration. We have a function f of x, which is a quadratic, x minus 3 times x plus 1, defined on the interval -1 to 3. Hey, that's kind of interesting. That looks like the roots of this quadratic. And in the first problem, we need to compute the lower and upper sums of f corresponding to the partition x equals, okay, -1, 2, and 3. Oh, that's a pretty easy partition to deal with. So why don't we start with the lower sum for f corresponding to this partition. So how do we define this? Well, for each of the pieces of this partition, so there's 2 pieces in this case, we're going to look, since this is a lower sum, at the infimum over all t between, well, for the first partition, or the first part of the partition, -1 to 2 of the function. And then we're going to multiply this by the width of this partition. So from -1 to 2, that has width 3. So we'd multiply this by 3. Okay, then we need to look at the second part of the partition. So we'll take the infimum over all t between 2 and 3 of f of t, and we multiply by the width of that part of the partition. 2 to 3 has width 1. So we just multiply by 1. Okay, not too shabby. Let's see. Well, we're looking at for the infimum, and maybe if we graph this, it'll be a little bit easier to see what's going on. We know this is a parabola. We know it has roots at -1 and at 3. Okay, so it's going to strike there. It's going to strike there. And this has going to have a leading term of x squared, which is a positive leading coefficient. So this is facing upward. So right down the middle, which I guess, let's see, that should be at 1. We're going to have a vertex somewhere down here. It doesn't really matter at the moment. We'll find out if we need to know the y coordinate. That's a y up there, by the way. So do we need to know the y coordinate of that vertex? Well, let's see. So 2 is over here. That's going to be important because, right, our partition is at -1, 2, and at 3. All right, so let's check it out. So on the interval from -1 to 2, the infimum of f of t is actually going to be the min value in this case. So, and in this case, I guess we do need to know. So let's see, when I make x equal to 1, the first part becomes 1 minus 3 is -2. Second part becomes 1 plus 1 is +2. Multiply those, I get -4. Okay, so the infimum on the interval -1 to 2 is -4. And of course, I'll multiply that by 3. Now when I move over to the interval 2 to 3, the infimum is going to occur, it looks like, yep, when x is equal to 2. And what is that value? So let's see, when x is 2, I get 2 minus 3 is -1, and 2 plus 1 is 3. -1 times 3 is -3. Okay, so the infimum on this interval will be -3. And so in total, I'm going to have -4 times 3, which is -12, and -3 times 1, which is -3. And so my lower sum for f corresponding to the partition x will be -15. Okay, not too bad. Why don't we try the upper sum? So the upper sum is going to look almost the same. I just copy everything except for the infs, which I replace with sups. Everything else is going to be exactly the same. Okay, we're copying. All right, so let's see, what are the supremums on these two different intervals? So from -1 to 2, well, the highest point is actually, well, at -1, where the sup is 0. Oh, so this term doesn't even contribute anything. Okay, what about from 2 to 3? Oh, well, from 2 to 3, I also get all the way up to 0. And so, in fact, my upper sum is going to be precisely 0 plus 0 equals 0. All right. Now, looking ahead, we know we want to get our upper and lower integrals to actually equal each other, and those upper and lower integrals are defined in terms of the upper and lower sums, and right now, these seem pretty far apart. Does that mean the function isn't integrable? Probably not, right? Like this is a continuous function. We know all continuous functions are integrable. The issue is we started with a partition that it's just not, it's not very broken up, right? Right? We called this a two partition. Okay, so this was a two partition of -1, 3. So unsurprisingly, we don't get the best estimates for the upper and lower sums. All right, so why don't we try part B now? So part B says we need to explain how we're going to determine whether f is integrable on -1 to 3. That is, we need to define the upper and lower integrals of f and state the condition that defines whether f is Darboux integrable. Okay, well, I kind of just said it, but we'll do it again. So the upper integral, or maybe we'll do the lower first. So if I was going to integrate from -1 to 3, this function f with respect to x, and I want to do the lower integral. Okay, so this is the lower integral, indicated with this underline on the bottom side. Well, what we want to do is we want to look at all of these lower sums. So I take LF of x, and then I want to take the largest of all of them, or actually even a supremum of all of them. So I take the supremum over all partitions of -1, 3. All right, and then the upper integral is defined in almost the same way. So I want to go from -1 to 3. I use an overline, so this will be the upper integral. Okay, this will be f dx. And this is defined, well, instead of the supremum, this will be the infimum over all partitions x from -1 to 3, but now of the upper sums for f. Okay, and the condition for integrability then, so f is integrable on -1 to 3 if this lower integral equals the upper integral. All right. And of course, in practice, we don't usually show this directly. Instead, we'll use the integrability criterion. So the integrability criterion is going to tell us, well, let's not try to make them equal, right? Like don't pull a hamstring or something, right? Let's just try to get them really, really close, no matter how close you want to get them, right? And so all we have to do is find some partitions so that the difference between an upper and a lower sum is bounded by some epsilon, right? So that's in practice what we like to do. Okay, well, there we go. That is how we would check whether or not f is integrable. All right, well, I guess we can move on then to problem 33. Okay, so in problem 33, we're going to be looking at some properties of the Darboux integral. Let's see, so we have a function f from a, b to r. And in A, we want to state a general condition on f that implies that f is Darboux integrable. Well, probably the easiest one we can write down is if we know that f is continuous. Right? So if f is continuous, then we were able to prove that f is Darboux integrable. All right, part B, if f has a discontinuity, then can f still be Darboux integrable? Well, we actually showed yes. In fact, if you have one discontinuity, you could still be Darboux integrable. In fact, if it's continuous everywhere else, it will be. If it has two, yep, it still will be. Even if it has any finite number of discontinuities, but it's continuous everywhere else, then f will be Darboux integrable. In fact, we were able to give an example in class where it was even discontinuous at a countably infinite number of points, and it was still integrable. This was the so-called Thomae's function. And in the second half of the class, we'll even do ourselves one better and show that there is a function that has an uncountably infinite number of discontinuities and is still Darboux integrable. Okay, but we're not to there yet. But the answer here, yes, it still can. In fact, yes, it is. If f is Darboux integrable, can we conclude that f is continuous? Well, actually, based on the previous one, no, right? If you have a discontinuity, you're still going to be Darboux integrable as long as maybe there's not too many of them. So the answer here is, can we conclude f is continuous? No. No, you can have discontinuous functions that are Darboux integrable. Finally, if we know f is integrable, and f of x is at least -30, in fact, greater than -30 for all points in the domain, then what is the largest real number that we know is less than the integral of f over ab? And so what we're working with here is that if -30 is less than f of x, then, well, what if I take -30 times b minus a? Okay, so this is the width of the interval. This is going to be less than the integral of f over ab. So this right here, this negative 30 times b minus a, is the answer to our question. That's going to be the largest real number that we know is less than this. And in fact, if you look at the special case where negative 30 was equal to f of x at some point, right? But it was like that was the infimum of f of x, all right? Then we actually would, if we started computing all these lower sums, well, this negative 30, right? That's the infimum for one portion. And so if I replaced all the other infimums with negative 30, I'm just getting a smaller answer, right? But it could be like maybe just everything is at negative 30, right? That could be also. So we can't do really any better than this. So there you go. That is the largest real number that we know is less than the integral. Right. But by the way, you might want to see a picture of something, right? So let's say I put negative 30 down here. The idea is if the graph is going to go down and well, maybe it never actually hits it there, right? There's negative 30. So maybe even it jumps up or something, a little discontinuity, doesn't really matter. And I want to go from like A to B. Then when I go to compute the integral, well, if I use instead of the actual integral, which would be giving me all this stuff here, if instead I just use a rectangle like this, and I say, oh, well, how much am I getting now? Well, I'm definitely getting some value, right? Very, very negative, and so it's going to be less than what I'd get if I integrated the f, right? That's the idea here. All right. Well, let's not belabor the point. Let's move on to problem 34. All right, problem 34. Let's see. We have, for x positive, we define a function L of x equal to, oh my goodness, it's the integral from 1 to x of 1 over t dt. Oh my goodness, look at that. It's an integrally defined function. Nice. Okay, part A says, which theorem implies that L is differentiable on the interval 0 to infinity? Well, of course, that is the first fundamental theorem of calculus. First fundamental theorem of calculus. Okay, so remind you, the first fundamental theorem of calculus, this is exactly defined for this situation. So if you have a continuous function, which 1 over t is, right? So on the interval 0 to infinity, 1 over t is continuous, then the first fundamental theorem says that this function we've defined, L of x, is an antiderivative for 1 over t. Okay, and if it's an antiderivative, that means it's differentiable. All right, fine. Part B says to compute L prime of 4. Well, that's the other part, right? If I know that L is differentiable and it's an antiderivative of 1 over t, well, then I can take its derivative. L prime of 4 is equal to, well, the derivative is just going to be this function 1 over t evaluated at x. In this case, it's 4. So 1 over 4. That's it. That's like the whole problem. How crazy is that? Right? Okay. First fundamental theorem of calculus. Yeah, tell your friends. All right, let's check out 35. All right, problem 35. We just need to state the second fundamental theorem of calculus. All right, let's see if we can do this. So let's see. We're going to let f be some function from the closed interval a, b to r. And we're going to assume that f is differentiable. So we're going to let this be differentiable with derivative f prime. Okay. And we're going to assume, right, that f prime also has domain AB. Okay, so derivative f prime, which also has the same domain. Okay, so we start with that. So we have this f prime, which we know because it's the derivative of f, we know f prime has an antiderivative. So if f prime is integrable, then the integral of f prime over this interval ab is simply going to be the net difference of its antiderivative, which is this original f, at the endpoints of the interval. Okay, there it is. There's the second fundamental theorem. So big notational difference between the way I like to do it and the way, for example, it's done in a lot of textbooks like Stewart is I don't like to use this capital F for the antiderivative. I instead like to note, like, I'm integrating a derivative. Because it's a derivative, it has an antiderivative. The notation tells me the antiderivative should be a little f, okay, instead of having to introduce a new letter. All right, so there it is. All right, well, we're going to move on to problem 36 now. And here we are in problem 36, our final problem on the exam at long last. Well, let's take a look at it. Does the second fundamental theorem of calculus imply that integration can always be done by computing the net difference of an antiderivative on the boundary points of the domain? And if we scroll back up to the second fundamental theorem of calculus, that sure seems to be what it looks like if I just focus on this. I want to integrate. I compute the net difference of an antiderivative at the boundary points of the domain. That's what it says, right? No, there's a lot more going on here. For example, well, first, f prime is integrable. Okay, so we better assume that that's true. But more to the point, f prime is an f prime. It's the derivative of some function. It has an antiderivative, right? And this statement down here is not saying integration can always be done to a function that has an antiderivative. It says it always can be done by computing the net difference of an antiderivative. Okay? And this is something we talked about a lot in class. It is a fundamental mistake to believe that integration is the second fundamental theorem of calculus, that integration is finding an antiderivative and then computing the net difference on the boundary points of the domain. It gives you the same answer as integration under certain conditions. Okay? They're not the same thing. We just have this wonderful theorem that says, hey, you're in the right situation. You can use the net difference of the antiderivative, ... Okay, so the answer here is no. And a good explanation or a good example of where you can't do it is this piecewise function we've seen in class a lot. So let's say you're at the value 3, and I'll say we'll start at 5, and then when we get up to 7, it's going to jump down to 1. And then it's going to go there until we get to, I don't know, 10, say. So I can very easily, I don't need any of this stuff, I can very easily integrate this function. We'll give a name to it, we'll call this h. And I can integrate from 5 to 10 this function h. Simply, right, I can just see the area of these things, right? This one is 2 by 3 is 6, this is 3 by 1 is 3, so this integral is 9. However, by Darboux's theorem, I know that h does not have an antiderivative. H has no antiderivative because it does not satisfy the intermediate value property. Okay, that's kind of it right there, right? So if h doesn't have an antiderivative, I can't use the second fundamental theorem of calculus. And yet I can still compute this integral. Okay, so integration happens whether you have antiderivatives or not, right? That's not the important feature. All right, well, thank you for going on this very long journey with me. We will see you next time.